Why is the sky blue? How do rainbows form? How do we know there's a nucleus inside an atom? How do we know there are quarks inside nucleons? The answer to all these questions is scattering, perhaps the most essential concept in all of physics. Think about it. What's the source of all your knowledge? Observation, measurement, right? You observe objects because light bounces off them and reaches your eyes. If there were no scattering, but only absorption and emission, we would not be able to see most non luminous objects. Here is the basic premise of scattering theory. You have an object that you want to study, for example, a proton. Right now, you know nothing about it. We call it a black box. You prepare an input, a beam of electrons, for example. Since you have prepared it yourself, you have complete knowledge of its properties, like intensity, wavelength, phase, etc. Next, you send this input into the black box and they interact. Something happens that we can't see. An output wave is then emitted, which you record using your detector. Now, you study how your output has changed relative to your input. Did the intensity change? Were there any phase shifts? Did new particles appear? From this comparison, you infer the properties and interaction potential of your black box. This is the essence of scattering theory. Learning about an unknown system indirectly through how it modifies a non-incoming wave. Why study scattering in quantum mechanics when we already have a classical theory? In the classical theory, we model scattering as collisions between billiard balls with well-defined trajectories. In the subatomic world, however, the rules of quantum mechanics kick in. Particles such as electrons behave as waves, which means the trajectories can be measured with only very limited accuracy. So when a quantum wave interacts with the interaction potential of a target, interference effects appear. In quantum scattering theory, we measure the resulting phase shifts and amplitude changes to calculate the potential. The historical significance of scattering theory is immense. From Rutherford's gold foil experiment that led to the discovery of the nucleus, to the deep inelastic scattering experiments at the Stanford Linear Accelerator that led to the discovery of quarks, scattering theory forms the foundation of modern physics. In this series, I will discuss the fundamental concepts of the theory and two key techniques, the Born approximation and partial wave analysis, as well as all the related concepts. This series is for you if you are bored by the lengthy derivations. I won't rederive every standard result from scratch. You can find them easily in standard textbooks. Instead, we will focus on the physical intuition behind the concepts. See you in the next video. Thanks for watching.